Okay, we're on to part 3 of 3 on my trig graph transformation series. In this video I'm going to do 3 more examples. I'll do cosecant, secant, and cotangent. If you are just watching this one as your first one, I would probably go back and watch part 1 first and then part 2. And I even have a video on sort of a GeoGebra program look at some of these trig function transformations, which is kind of cool, so check that one out too. But what you missed in part 1 particularly is when we take a trig function and we add all this other stuff to it, right? I'm not going to go into too much detail right now, but this a value, that changes the amplitude. It changes the amplitude or the height of the graph. This b value, that changes the period of the graph. This c value, that changes the horizontal shift or the phase shift of the graph. And this d value, well, that's going to change the vertical shift or the vertical translation of the graph, right? And if you're looking for more detail on exactly how those things work, go back and start with part 1. But in this case, we don't have sine, we have cosecant, which is the same thing. Right? They're acting a lot of the same ways. So let's take a look at this one. We'll start with 2 cosecant x minus pi over 2. So first and foremost, the amplitude kind of gets bumped up by 2. Right? That's my a value that changes the sort of the stretched out, the vertical stretchiness of the graph, if you will, or the height of the graph, right? But cosecant to begin with doesn't have an amplitude, so this one's not either, but I am going to sort of put in parentheses here that it gets sort of stretched out, stretched by a factor of 2. This is my c value. It's minus, which means I'm moving right. This is a phase shift. I'm moving right pi over 2. All right. So my normal cosecant graph, I always like to kind of maybe start with that. My normal cosecant graph it's undefined at 0, right? And it comes all the way down here, and it goes back up. This is an asymptote at pi, and then at pi over 2, it's down this way, right? Everywhere, this is the 1 over sine. Cosecant is 1 over sine. So everywhere that the sine is 0, which is right here, at pi units and at 2 pi units, everywhere the sine is 0, the cosecant doesn't exist. All right, so this is my normal cosecant graph. Well, if I multiply that by 2, then all of a sudden this thing gets just bumped up like that and bumped down like this. So that's what changing the a value does. All right, and if we then affect the phase shift, then all of a sudden I need to take that whole thing and I need to move it to the right pi over 2 units, which will be somewhere in there. All right, so I'm not going to actually do it like that. I just wanted to give you a general idea of what our plan was. So let me erase, because I need to get rid of the asymptotes and kind of change those as well. But we're changing the amplitude, the a value rather, and we're also moving this thing right pi over 2. Okay, so first and foremost I need to get my scaling down. My period hasn't changed. My period is the same as the regular cosecant, which is 2 pi. So if I make this pi over 2, that means this would be pi, this would be 3 pi over 2, and this would be 2 pi. If it starts here, then it has to end at 5 pi over 2. That's not, I don't have enough space on my graph, so I need to kind of change my scaling. I need to change my scaling, and maybe I'll make this pi over 2 right there. So maybe I'll make that pi over 2, which means this is pi. 3 pi over 2. 2 pi. 5 pi over 2. Alright, so the period now, and I guess I could have changed that a number of different ways, but the period is going to go from right pi over 2 all the way over to 5 pi over 2. In other words, the difference between those is 2 pi. The asymptote then starts right here at pi over 2. And the next one's at 3 pi over 2. And 5 pi over 2. Alright, and if you want to actually plug these in, you certainly can. Check pi over 2, right? 2 cosecant of pi over 2 minus pi over 2. Well, that's 0. Cosecant of 0 doesn't exist, which means there's an asymptote. Same thing would happen if you plugged in 3 pi over 2. 3 pi over 2 minus pi over 2 is pi. Right? Sine of pi is 0. Cosecant of pi does not exist. There's an asymptote. 5 pi over 2, same deal. Okay, so we've got our asymptotes in there. And like I said, it just kind of gets bumped up. Normally it goes down here to positive 1. But now it's going to get bumped up to positive 2 and bumped down to negative 2. And there's the bell, sorry. I'm at school right now. So here is pi comma 2. So that goes up this way and up this way. 2 pi negative 2 goes down this way and down this way. All right, we can check that just to make sure. If we plug in pi here, 2 cosecant of pi minus pi over 2. What is this? Well, it's common denominator is 2 pi over 2 minus pi over 2. That's pi over 2. So 2 cosecant of pi over 2. Well, the sine of pi over 2 is 1. So the cosecant of pi over 2 is also 1. 2 times 1 is 2. Does that make sense? That's where we're getting these y values. You literally plug the value in, plug the angle in, and see what happens. So there you go. The domain is all real numbers. And remember, this would go on forever. Right? It would keep repeating itself. This one would go down here, right? And this one would go over here, and it would keep repeating forever and ever. Right? So the domain is everything, except where the asymptotes are. And the asymptotes occur, the first asymptote, so it's all real numbers. Let me get rid of this amplitude note. It's all real numbers except x cannot be the first asymptote, and then every other time an asymptote occurs, which is pi times n, where n is an integer. N's a positive or negative number. So there's an asymptote that occurs over here as well. And so on and so forth. The range is kind of interesting. It's negative infinity to negative 2 inclusive, and then it skips and goes from 2 to positive infinity. Remember, the range is the y values. X-intercepts, there aren't any. Maximum, I don't know. That's kind of a funny question here, but I would say that it's down here. 2 pi comma negative 2. It's not a super common question for this, but I suppose it does apply. The minimum value is, of course, these are relative or local extrema. Pi comma 2. Asymptotes, there are definitely asymptotes. Pi over 2, 3 pi over 2, and 5 pi over 2. And there are obviously an infinite number, but those are the 3 on my screen. Phase shift, we already said this goes right pi over 2. Vertical shift, there's not any, and there's no reflection either. So there you go. Moving on. Alright, so here we have negative secant x over 2. So right away I see my reflection because I have a negative a value. So if the normal secant kind of looks like this, that's a terrible graph, but if the normal secant kind of looks like this, and then it goes over here, and does something like this. That's the normal secant. The reflected version is just going to be that thing upside down, and this thing right side up, kind of, something like this. So there's the reflected secant, reflected over the x-axis. Now this x over 2 business, that changes, so my b is 1/2, right? X over 2, my b is 1/2. This is another way of saying like 1/2 times x. So if my b value is 1/2, then my period changes 2 pi divided by 1/2. I'm using 2 pi because that's the normal period of the secant function. Well, that's just 4 pi. So my period is actually bigger, even though this is a fraction. My period is actually twice as big as it normally is. Amplitude doesn't really apply for these because there isn't any. Domain will come back to, range will come back to. So let's actually graph this thing. We have our general shape down. Right? We talked about the fact that it's reflected. We also need to talk about the fact that it has a much bigger period. So the normal secant graph would be like, this would be negative pi over 2. This would be pi over 2. And this would be, let's see, this is pi, so this would be pi, and this would be 3 pi over 2. That's normally one cycle of the secant that would be flipped over. But our period is twice as big as that. So what you can do is just keep the general graph that way and change your x-axis scaling. All right, so this needs to be changed. If it normally is 2 pi, now we want to make it 4 pi. So instead of taking this left pi over 2, let's take it left pi. That means this is pi right here. That's pi. This is 2 pi, and this would be 3 pi. So the period there from here all the way over to here is 4 pi. Now that's kind of cheating because I didn't really change the look of my graph, but I don't really think that that's a huge deal, simply because the period's kind of really big and I don't have like a ton of graph paper, so I'm kind of okay with what I just did. I'm just going to maybe clean these graphs up and make them look a little nicer. Let's make it look a little nicer here. I was going a little fast last time. That's pretty good. And I'll take this one down here and draw like this. And I'll finish my asymptotes off as well. And maybe make them look a little nicer. Now if I had more graph paper, I would draw a nice comparison between the original secant and this one, just to get a really nice idea that the period is twice as big. So this would be kind of like really stretched out this way. Alright, but I kind of cheated a little bit and just changed my x-axis scaling, which is fine. Nothing wrong with that. Now really quickly, there's some of these key points, right? If I plug in 2 pi here, negative secant of 2 pi over 2, well the 2's cancel, so it's really just asking what's a negative secant of pi. Well, to think about secant of pi, I maybe want to think about cosine of pi. The cosine is the x value, pi is over here. The x value is -1. So the secant value is -1 as well. 1 over -1. Negative -1 is +1. That's where I'm getting that y value right there from. All right, so if you ever get confused about some of these, just plug them in. See what y value you get. But I think this is pretty good. Right? This is a pretty good representation of this graph. So I will move on to the next one. Well, let me answer some of these questions first. The domain, all real numbers, with the exception that x cannot be pi. That's my first asymptote. And it cannot be 2 pi thereafter. In other words, if I take an integer, positive or negative whole number, and multiply it by 2 pi and add that to where I started, that gives me another asymptote. Think about it. Pi plus 2 pi is 3 pi. Pi minus 2 pi is negative pi. The range is negative infinity to negative 1 inclusive, skips over 1 to positive infinity. No x-intercepts. Maximum, I guess you would say that would be 0, negative 1. That's a relative maximum. Minimum value is 2 pi negative 1, or positive 1. That's the lowest value of any point near that point. Asymptotes, of course, we have negative pi, pi, and 3 pi. X equals on all those since they're vertical lines. This thing didn't phase shift and it did not vertical shift. It reflected and the period doubled. So there you go. Last one. Alright, so this one looks like a b value of 1/4, a c value of pi over 4, and a d value of negative 1. Okay, so we have a couple things changing here. Let's start with the most obvious one, is the vertical translation. That's down 1 unit. The period is changing, right? It's normally in cotangents normally pi units. Well, so that's going to change this pi over 1/4, which is 4 pi. So my period is 4 pi. Now be careful, I'm starting with pi as my numerator because that's the normal period of cotangent. Right, in a previous video we studied cotangent in its regular form and determined that the period was pi. So you take the period divided by the number here. So we get 4 pi. Then we want to look at the phase shift. The phase shift is right, and then it's c over b. So it's this number over this number. Alright, so it's pi over 4 over 1/4. Okay, interesting. Pi over 4 over 1/4, well, that's just pi. Pi over 4 divided by 1/4. Pi over 4 times 4. Keep it, switch it to multiplication, flip it over. So the 4's cancel out. So we're dealing with a period, a phase shift right pi units. Right pi units. So I'll write that down here. Phase shift right pi units. Okay. As always, it's probably a good idea to get a general idea of what cotangent normally looks like. In cotangent, this is pi over 2, and this is 1, this is negative 1, and we have asymptotes. So it generally looks like this, cotangent normally. So this one is going to be, that's a period of pi. This is pi, right? So from 0 to pi, it repeats itself. It would keep going over and over again. All right, but this one's going to repeat itself every 4 pi units. So I need to somehow take this thing and make it look like that, something like that, maybe more. But I don't have room for that, so I'm going to kind of have to be a little bit tricky with my x-axis scaling. And then I also have to take the whole thing and I need to move it right pi units. So that would be like doing that, and then down 1 unit. So there are a couple things I need to do for this one. So let's go ahead and get started. I need to go and I need 4 pi units, and I need another pi units, and I need to make sure I go down 1. So if I make, let's see, if I make this right here 4 pi, that means this would be 2 pi, this would be 6 pi, this would be 5 pi. Right? If I mark my x-axis like this, let's see how this looks. It's a little cramped, but that's okay. And my normal asymptote is right here at 0. So I need to move that over to pi. So let's put that right here. Alright, and now my whole function needs to repeat itself every 4 pi units from there. So what's 1 pi plus 4 pi? It's 5 pi. So there's my second asymptote. So one cycle of cotangent is going to repeat itself within those sort of barriers. Alright, so if I split that in the middle, I get 3 pi. Alright, but then I need to move it down 1. So down 1. So let's put it right down here. So let's make this -1. This +1. And I don't have to have my x and y axes scaled the same. I can scale my x-axis this way, right? So this is like 24. 8 times pi is about a little over 24. And this is only 3. Who cares? I'm making this up and I'm totally cool as long as I'm consistent vertically and I'm consistent with these intervals. Alright, these increments are really important. Alright, so I think I have my center point for cotangent. Now all I need to do is think about the fact that it's going to be shaped something like that. So with tangent and cotangent, there are 3 points that are really important. Once you get your asymptotes, you get your middle point, and then you want to think about the value right here and the value right here. So in other words, if I plug in 2 pi, cotangent of 2 pi over 4, I'm plugging in 2 pi for this, minus pi over 4 minus 1. Let's literally just calculate it. 2 pi over 4, that's pi over 2. Let's figure this out. All right. Combine like terms, or get the denominators rather, common denominators. So 2 pi over 4 minus pi over 4 is pi over 4. So I need to know the cotangent of that, minus 1. Well, to know the cotangent of that, think about what the tangent of pi over 4 is. It's 1. So the cotangent is 1 over 1, which is still 1. So 1 minus 1 is 0. So there's an x-intercept right there. If I do the same thing for this important point, if I plug in this time, if I plug in 4 pi in my numerator, that means this is just pi. The 4's cancel. So I have 4 pi over 4 minus pi over 4. That's 3 pi over 4. 3 pi over 4. Well, 3 pi over 4 is, 3 pi over 4 is in my second quadrant with a reference angle of pi over 4. So I know it's 1, and it's second quadrant, only sine and cosecant are positive, so this is -1 minus 1. That's -2. So that's down here. All right, look at that symmetry. From here to here to here. They're all equidistant. Everything's nice. So let's connect them. Something like this. So I think that looks pretty good. Let's just check to make sure that this value is accurate. So if I plug in cotangent, let's see, if I plug in 3 pi over here divided by 4, I'm plugging in 3 pi right here, minus pi over 4 minus 1. So this is 2 pi over 4, which is pi over 2. The cotangent of pi over 2, let's see, the tangent of pi over 2 is undefined. Now the tangent of pi over 2 is, let's see, sine over cosine. The sine of pi over 2 is the up and down direction. That's -1. That's undefined. Yeah, I was right. So this is 1 over, or no, this is 0 over 1. So that's 0 minus 1. Yeah, that makes sense. 0 minus 1. Perfect. So I was right. All right, life is good. We are ready to wrap this up here. We have our 3 key points. We have our asymptotes. Amplitude, there isn't any for this. Cotangent, tangent, secant, cosecant don't have amplitudes. Domain is all real numbers with the exception of the asymptotes. So that's pi plus 4 pi times n, where n is some positive or negative whole number. The range is everything. X-intercept, you can see right there, was 2 pi, comma 0. No maximum, no minimum. Asymptotes, definitely pi and 5 pi. And this is not reflected. Okay, so I am finished. That wraps up part 3. That's about a 26-minute video. That's a lot. I'm kind of tired, but hopefully I didn't make any mistakes. So thanks for watching. Again, I have the previous 2 parts that were a little bit easier than this one, that dealt with sine, cosine, and tangent. This one dealt with the 3 reciprocal functions. I also have the GeoGebra video that's definitely worth checking out if you're confused about some of these. But from here I'm moving on into trig identities. I'm going to do a 3-part video series on verifying trig identities, so look forward to that. Thanks for watching.